Welcome to the June 2020 edition of AJP-Heart and Circulatory Physiology Video Table of Contents, or from the editor's desk. We sincerely hope that everyone is in good health and maintaining social distancing and everything else that's necessary to combat the current pandemic. Casey and I are making the best of it, right, buddy? And we're at home. So we invite you to browse this month's issue here, and here's a little sample of what's inside. In a Perspectives article, Pechana et al. Discuss the global burden of physical inactivity on cardiovascular disease as a result of the COVID-19 pandemic. Confinement-induced decreases in physical activity levels and increases in sedentary behavior may provoke a rapid deterioration of cardiovascular health and premature deaths among populations with increased cardiovascular risk. Even short-term, 1 to 4 week inactivity has been linked with detrimental effects in cardiovascular function and structure and increased cardiovascular risk factors. They discuss the benefits of home physical activity. This paper is, of course, highly relevant to the majority of the global population. Musa et al. Examined myocardial expression of synapse-associated protein 97, or SAP97, a scaffolding protein crucial for the functional expression of several cardiac ion channels and therefore proper cardiac excitability. In this study, they generated a murine model for inducible cardiac-targeted SAP97 ablation to investigate arrhythmia susceptibility and the underlying molecular mechanisms. SAP97 ablation demonstrated several ECG abnormalities, pronounced action potential prolongation, subject to high incidence of arrhythmogenic after depolarizations, and notable alterations in the activity of the main cardiac ion channels. Furthermore, they identified high SAP or a DLG1 variant in humans that were associated with inherited arrhythmogenic disease. Rutkai et al. Report the first in vivo imaging of mitochondria specific to the cerebral endothelium in real time in the same mouse for extended periods. Mice expressing dendra-2 fluorescent protein in mitochondria, or mitodendra-2, in the cerebral vascular endothelium were generated. They used mitodendra-2 expression, a cranial window implantation, and 2-photon microscopy to visualize mitochondria in the cerebral vascular endothelium of mice. Mitodendra-2 and rhodamine B conjugated dextran allowed simultaneous determinations of mitochondrial density, vessel diameters, area, and mitochondria to vessel ratio in vivo, repeatedly in the same mouse. While the overall mitochondrial signal was stable over time, mitochondria within the same endothelial cell were mobile. These results indicate that the mitodendra-2 signal and vascular parameters are suitable for real-time and longitudinal examinations of mitochondria in vivo in the cerebral vasculature of mice. Ashton et al. Examined the potential role of cardiac ganglionic plexi neuronal plasticity in atrial arrhythmia and hypertension. They used whole cell patch clamp recording techniques from ganglionic plexus neurons in isolated intracardiac nervous system preparations from aged control Wistar Kyoto and spontaneously hypertensive SHRs. Whole cell recordings revealed elevated spontaneous postsynaptic current frequency in SHR neurons, as well as remodeled electrophysiology with significant decreases in action potential amplitude and half-width. SHRs also showed a parallel increase in the number of cholinergic neurons and adrenergic glomus cells in cardiac ganglia, a higher proportion of synaptic alpha-7 subunit but not beta-2 containing nicotinic receptors, and an elevation in the number of synaptic terminals onto ganglionic plexi neurons. In a rapid report, Ebner and co-workers explored the hypothesis that dystrophin-deficient cardiac Purkinje fibers have reduced sodium currents, which would represent a potential mechanism underlying slowed ventricular conduction in the dystrophic heart. They isolated Purkinje fibers from the hearts of adult wild-type control and dystrophin-deficient MDX mice. They found substantially reduced sodium current densities in MDX compared to wild-type Purkinje fibers, suggesting that dystrophin deficiency diminishes sodium current. They proposed that reduced sodium current in Purkinje fibers at least partially explains impaired ventricular conduction and the associated arrhythmias in the dystrophic heart. McAllen-Hart et al. Tested the hypothesis that decreased coronary resistance microvessel stiffness in type 2 diabetes is due to reduced vascular smooth muscle cell stiffness, which impacts the traction force generated by vascular smooth muscle cells. Atomic force microscopy and traction force microscopy were conducted on primary low-passage coronary resistance microvessel smooth muscle cells. From normal DBDB and type 2 diabetic DBDT mice, both mouse and human type 2 diabetic coronary microvascular smooth muscle cells were less adhesive to fibronectin compared to normal type 2 diabetic DBDB coronary vascular smooth muscle cells generated enhanced traction force by traction force microscopy. Immunoblot analysis showed that type 2 diabetic human coronary vascular smooth muscles expressed reduced beta-1 integrin and elevated beta-3 integrin. Casey and I want to thank you for watching. Please stay safe and send us your original cardiovascular research. We promise you a fast turnaround time. We'll see you next month.